So here in this lecture, we will talk about some applications of mixed integer linear programming. As I said, this is one of the most widely applied optimization problem. Here we will talk a few examples. The first four applications are very widely known in the operations research community, like traveling salesman problem, facility location, lot sizing, and scheduling problem, right? Those problems have been very widely studied by the operations research people or the applied mathematicians. So the fifth problem, unit commitment, is an application in electrical engineering. But I think it's worth knowing that because some of the other engineering problems can be formulated very similar to the unit commitment problem. And finally, we will talk about an application specific to chemical engineering, meaning that we are using optimization to design chemical flow sheet. But in other engineering disciplines, there are similar problems as well. Okay, so what is the traveling salesman problem? You might have heard about it in other lectures. It says a salesman would like to visit n cities sequentially, right? If you imagine if you are, let's say, a truck driver for a company like Amazon or FedEx, like each day you have a number of packages to deliver to end customers, right? And of course, you want to find the shortest path to visit the end customer, right? That is the so-called traveling salesman problem. It has very wide applications in logistics, manufacturing, storage, and actually it also has application in scheduling. How many of you work with Professor Joe Packney? Only you, right? So one of his early work during his PhD is that he used the traveling salesman problem to solve a scheduling problem, right? He developed a very smart way of formulating some chemical process scheduling problem in terms of the asymmetric traveling salesman. Okay, you can ask him over your meeting. Okay, yeah. Then let's talk about how to formulate this problem. Actually, there are more than 10 different ways you can formulate traveling salesman problem as an MLP, but we will talk only about one of them. Okay. Of course, in order to describe this logic, you need some sort of binary variable, right? So let's define a binary variable x sub ij equals to 1 if the traveling salesman travels directly from city I to city j, right? Suppose you have a number of cities, and then you want to decide the sequence you visit those cities, right? So if xij equals to 1, that means this path, or in a graph, it will be an edge, right? This edge from I to j is chosen, right? And it's 0, meaning that this edge from city I to city j is not chosen. The objective is to minimize the total travel time, right? So let's suppose if you pick 2 points, the travel time is deterministic, right? In practice, it's not deterministic, right? If you drive from home to your office, each time you take a slightly different time, right? But let's assume the traffic is very mild and the time is deterministic now, right? And the objective is to minimize the total travel time, which will be the sum over Cij xij, right? Okay, if the path is chosen, that will be 1, then you have the travel time Cij sum into the objective. Okay, and this function calculates the shortest possible route to visit each city once and then return to the starting point. If we have Cij equals to Cji, it is called a symmetric traveling salesman problem. What does that mean? That means if you drive from home to office and from office back home, the time is identical. For most problems, this is not the case, right? You are taking a different path when you drive back. And then if not, this is so-called asymmetric traveling salesman problem, right? Cij is not equals to Cji. Yeah, so with that, we can think about what type of constraints we need to enforce, right? So here we have the objective and the variables. Then we can kind of guess what type of constraints we need to enforce, right? The first thing you should think about is that we are exactly visiting each city once, right? You are not, let's say, visiting a city multiple times, right? So having said that, then we can have the first two constraints called, let me zoom in a little bit. This is the so-called assignment constraint, meaning that, let's say if you focus on a given city I, so let's say this is a given city I, right? And then after you visit city I, you can potentially visit different cities, right? Let's call them, let's maybe call them J1, J2, J3, right? So after leaving city I, you can only visit one of the cities other than city I, right? So that's what this constraint says. If you sum over xij, that j is not I, it should be equal to 1, right? So after leaving city I, you can pick another city to visit. Okay, that's what this constraint says. Any questions here? Yes.
So basically, you're just saying that we're going somewhere else.
Yeah, you are going somewhere else after. Yeah, right. Maybe pick a very concrete problem. If you have let's say 4 cities, you start from let's say this is where you start. After you visit city, you have 3 options, right? You can go to any one of these 3 cities, right? That's basically says you maybe you define them as 1, 2, 3, 4. That basically after visit city 1, you can go to any of these 3. It would be x12 x plus y x13 plus x14 equals to 1. Right? That's what essentially it says. And similarly, you can define the other constraint saying that if you are at a given city I, you must have visited some other cities before you arrive in city I, right? That would be, here we are fixing an index j. Okay, maybe I should use j instead here. So here, let's say we have a city j. Then maybe before visiting city j, you visit city I equals to 1, I equals 2, I equals to 3, right? Then the sum of those xij has to be equals to 1, right? So these 2 constraints essentially says after visit a given city, you have to go to another city that are not this particular city, right? And if you are at a particular city before visiting it, you must come from one of those other cities. Okay, that's what these 2 things says. So now let's think a little bit about with these 2 constraints, is it enough to enforce a traveling salesman constraint? Are there any issues with just these 2 constraints, right? Because intuitively you can think about if you only have these 2 constraints, each city is visited exactly once, right, with these 2 constraints. Yes?
Here you could have like discrete cycles.
Yeah, exactly, right. So that's exactly as you said. If you have only these 2 constraints, you may have some, in traveling salesman problem, this is called a subtour, right? So for example, in this figure, there are in total 11 cities, right? So you want to have a traveling salesman tour of the 11 cities, but if you only have these 2 constraints, this would also be a feasible solution to the TSP problem, right? In this particular solution, each of the cities is visited exactly once, right? You just go from 1 to 10 and come back, right? But actually, we want something like this, right? You have a single tour that visit all those cities, right? You don't want, you have to start with somewhere. You cannot have disconnected tours. Okay, so in order to eliminate this type of subtours, we have to add those constraints called subtour elimination constraints. Okay, so what does it mean? So here, if you look at this constraint, we have S here. So S is a subset of N, yes.
Why do we want to eliminate the subgroups?
Yeah, because you want to start from a given point and then visit N cities sequentially, right? Yeah, this subtour is not a feasible solution, right? You can, after you visit 1 to 10 and come back, you still have to go to all the other cities, right? The traveling salesman problem is a single tour. You have to visit all the N cities sequentially, right? But this is like you visit one and then you come back. You haven't visited other cities. Yes.
Any combination of these nodes can form a subtour, right?
Yeah, exactly. Yeah. So any combination of these nodes can form a subtour. That's why when you form the subtour elimination constraints, you are taking all the subset of N to eliminate those subtour, right? As you can imagine, there will be exponential number of subset of N, right? When you take a subset of a given set, you have 2 raised to the power of N subsets, right? That's a number of constraints we are talking about. That makes the traveling salesman problem very hard, right? So here, if you look at the subtour elimination constraint, what it does is you pick any subset of N where the size of this subset is between 2 and N minus 1, right? Why don't you include N? Because N is a feasible solution, right? If you take all the N cities, that is a TSP tour itself, right? So that's why you pick N minus 1. And what it says is if you sum over all the edges in this subset, they have to be less than equal to the cardinality of the subset minus 1, right? Okay, so if you look at this picture, if you pick node 1 and 10, then the cardinality of the subset is 2, right? Basically, this constraint says is all the edges within this subtour has to be less than equal to S minus 1, that would be 1, right? The number of edges is less than equal to 1, then that eliminate this subtour, right? This subtour has 2 edges being chosen, okay? Yeah. Okay, and then you can apply it to all the subsets except S is a full set or a single city. That's trivial, right? Okay, so any questions regarding the constraint? Yes?
What is the other constraint that besides the sequence? Like for example, in that graph,
Yeah.
Some numbers were closer to each other.
You mean
How is that?
after you solve the problem, how do you get the sequence?
No, like, for example, if I want to minimize distance that I'm traveling,
Mm-hmm.
and 10 is closer to 1 than 2,
Mm-hmm.
so then I would obviously prefer to go to 10 first and then 2.
Uh-huh.
Like,
No,
is there an extra constraint like that?
That could be some sort of tightening constraint, but there are combinatorial number of ways of picking that, right? Because once you go to, let's say, if you from 1 you go to 10 or 11, although 11 is closer than 10, that might not be the best way, right? Because that will affect how you visit other cities as well, right? There are combinatorial ways of choosing the tours. Okay, yeah. Other questions here? Yes.
Just to make sure I get this, there's an exponential number of these constraints.
Yeah, exactly. Yeah. Okay. Other questions here? Okay, so finally, I want to make this argument. It suffices to enforce the subset of N such that the cardinality of S is less than or equal to 1/2 times N, right? Why is that?
You did the complement as well.
Yeah, exactly right. Let's say if you have a subtour with size greater than or equal to half of N, right? Then if you have a tour, let's say, maybe let's pick a very concrete number. Let's say if there are 10 cities, what I'm arguing here is that you only need to eliminate the subtour with less than or equal to 5 cities. Because if you want to have a subtour with over 5 cities, let's say 8 cities, then you must have a subtour with 2 cities, right? So the subtour of 2 cities are already eliminated with S smaller than or equal to 0.5 times the N. Okay, that's some trivial comment here. Then the other comment I have to make is when you actually want to implement this, you don't want to add an exponential number of constraints, right? So how do you add those constraints? That's something we will talk about in the second half of the lecture. Actually, you only add the constraints when they are violated, right? Okay, no. You might be confused, but the way you, let me talk about it for 1 minute, then you will learn about the details in the second half of the lecture. So there is something called a lazy constraint in the solver. What those lazy constraints mean is they will only be enforced when the solution violates them, right? So now let's say if you have a piece of Pyomo code, you add all the constraints, then all of them will be enforced, right? But now I have too many constraints. If I enforce all of them, the solver will be stuck, right? So what I will do is that I add those subtree elimination constraint as so-called lazy constraint, meaning that if the solution doesn't violate those constraints, I'm not adding them. So they will only be automatically added if I check that the current integer feasible solution violate those subtree elimination constraints. We will come back to it at the latter half of the semester. Okay, so the second problem is so-called uncapacitated facility location problem. It involves determining the optimal depot and client servicing in order to minimize the cost. Okay, so maybe let's draw a picture to help you understand what it means, right? So let's assume we have a number of clients we want to serve using, let's say those are clients, and these are the potential depot locations. Let's say okay. So you can imagine, let's say we have a company like Amazon, right? You want to serve all the clients. In this case, the clients being regular customers like ourselves, right? But how does Amazon deliver those packages to each of its customers? The way it does is that it will open some facilities at each, let's say maybe at each given states or even each cities, right? Then it will store almost all its product at those facilities, right? And then whenever a customer needs this product, it will ship from the closest facility, right? Another question is, where should we build those facilities, right? Such that the distance is closest to the customers. In this problem, the purple circle are denoting the clients, and then the right rectangle is denoting the depot, potential depot location, right? We don't know what will be the best place to build a depot, right? Okay, that's why we are solving an optimization problem to decide what are the best way to build those depot, right? Okay, and if you want to build a depot, you will be charged with a fixed cost, right? Once you establish a depot, there will be a fixed cost. But on the other hand, if you build too few depots, the distance would be too high. You will pay extra transportation cost, right? So let's say for the sake of the argument, you only build this single depot, then the distance of this single depot will be pretty far from this point. On the other hand, if you build all the 3 depots, then you are paying a large capital cost, right? So there will be some trade-off in building more depots or minimizing the transportation cost. The facility location problem is solving this type of problem, okay? Now to summarize, so there will be a fixed cost Fj for depots and the transportation cost of Cij from depot J to client I. Okay. Any questions for the problem statement itself? Okay. Yeah, now we define some binary variables. Xj equals to 1 means that the depot J is used. Otherwise, Xj equals to 0. Then Yij represent the fraction of client's i's demand satisfied from depot J. Okay. So this is a so-called incapacitated facility location problem. We assume, each of the depot has unlimited capacity, right? That's why we are using the fractional of client's demand. We are not explicitly talking about how much the demand is, right? We are using a fractional number here. So now when we talk about the constraint, the first is demand satisfaction, right? Meaning that the demand of the customer have to be satisfied by all the depots, right? That will be the sum of Yij over j from 1 to n has to be equal to 1, right? So Yij denote the fractional of demand satisfied by a given depot. If you sum over all the depots, then you satisfy the demand of a given client, right? And here we have a depot client link constraint. And of course, if you do not build a given depot, then it cannot serve any customers, right? So here it says the sum over Yj would be equal to 0. So if Xj is 0, then all the Yij's has to be equal to 0, right? And y has to be greater than equal to 0 because they are demand fractions. Yeah, that's pretty much all the constraints you need to have for an incapacitated facility location problem. Yes.
Can you explain the depot client link again?
Yeah. So the link would be if you let's say you focus on a given depot. I draw the depot in red. Okay. So let's look at a given depot J. Okay. And then the purple dots are all the clients Y. So those are the so this is let's say client I. So Yij is a fraction of demand by client I that is served by depot J, right? So if this depot J is not built, all those Yij's connected to this depot J would be 0, right? Since the depot is not built. Okay, and that says if you sum over all the Yij that are assigned to this depot J, they should be 0. So M is just like a large number, like a big M parameter you pick. Okay, and there are, I will show you later, there is another way of formulating this problem, right? You can also formulate this constraint as Yij less than equal to Xj for all I in M, right? So the logic here is if this depot is not built, then all those links should be 0, right? So you can either write this as M constraints or as a single constraint, right? What are the difference? The difference is that here you have more constraints, but this formulation is tighter than the big M, right? You can show that you can derive the big M from those M constraints, but you cannot do it the other way around. It's just another thing to keep in mind. Okay, yes?
Does this also take into account the product the customer is more likely to buy? Like,
yeah, this doesn't. They just this is just like treat all the product equally.
okay.
Yeah, but what you said can be an extension of the facility location problem. Okay. Yes.
What do you mean by the fraction of demand?
Oh yeah. So yeah. So let's say if you look at a given, we focus on a given client here, right? You just treat the demand of client I as 1. And then look at all those, okay, so now we are focusing on a given client. Then the demand of client I is being treated as 100%. The fraction means the percentage of demand of I that are served by the 3 different depots you have, right? So that's why the sum of them has to be equal to 1. You are not explicitly counting their quantity. You are just treating the whole demand as 100%. Okay, so that means the sum of Yij here, Yij over J has to be equal to 1, meaning that the 3 depot will fulfill the demand of client I. Okay. Other questions here? Okay. Yeah, and then the objective involves the transportation cost and the fixed cost of building the depot, right? This transportation cost may be related to the distance, right? The Cij times Yij. I want to make another comment here is facility location problem is equivalent to K-Maddox clustering in machine learning. Right? Some of you might have taken a machine learning class and you heard about a clustering problem. Right? The idea is you have a bunch of data points. Right? You want to cluster those data points into different subgroups. Right? And you want to minimize the deviation of the data points within each of the subgroup. Right? And when you minimize the distance, you are kind of selecting the facility to build in those data points such that the distance of the data points in the same group to the center point is minimized, right? So here, you can treat the depots as the Maddox, and the distance would be the transportation cost, okay? And in K-Maddox clustering, each cluster is represented by one of the actual data points. This is analogous to you just select the depot to serve as the center of each of the cluster. Okay. This is just for people who have learned about clustering before in machine learning. It's a good analogy here. Okay. Yeah. So here I'm talking about an alternative formulation. Without using the big M, you can just force the Yij to be less than or equal to Xj. This constraint is saying that when a depot is not built, then all the links related to this depot would be 0, right? And this is tighter than the big M formulation, but has a larger number of constraints. Then we are going to talk about another problem called incapacitated lot sizing. It involves deciding a production plan for a single product over a given time horizon, right? So let's suppose you are operating a given plant. You only have a single machine to produce a single product. You can either produce a lot of product and then put that into the storage, right? And then when customer demand comes, you sell it in the storage, but you have to pay the storage cost. On the other hand, you can decide saying, I'm only going to produce that when the customer demand comes, right? And then you have to pay more production costs, right? Because each time you start the machine, you have to pay a fixed cost of starting the machine, right? So there are some trade-offs in doing there. The parameters given are the fixed production cost. So the fixed production cost means that each time t, if you start this machine, you have to pay a fixed cost no matter how much you produce, right? And the unit production cost is like the variable cost of producing this product. That means that this cost is proportional to the amount of product you produce at a given time. Okay, and we have the unit storage cost. Let's say if you overproduce, then you are putting that in a storage tank. You pay a unit cost for storing your product in a given tank, right? So if you want to make an analogy in chemical engineering problem, let's say you can produce things like hydrogen or ammonia or whatever, right? If you overproduce at a given time period, then you can put that in a storage tank. And then when the customer demand comes, you sell that from the storage tank. And demand T of the demand of the customer is denoted as the D sub T. We also have a production capacity. It's very easy to think about. Whenever you are running a plant, it has a maximum production capacity at a given time point, right? Now the variables we are going to define include the amount of product produced in time period t and the stock at the end of time period t. So we also define some binary variables xt. So xt is 1 if we are producing at time t, 0 otherwise. And the idea of this lot sizing problem is to balance the trade-off between the storage cost and the production cost. You will see that in a second. Okay. The objective function is to minimize the total cost, include the production, storage, and the fixed cost. First constraint we have is just a mass balance equation, right? So remember, St is your storage level at time t, right? Yt is the amount you produced at time t. So the storage at the previous time point plus what you produce will be equals to the storage at the next time point plus the demand, right? So we assume you always have to satisfy the demand with what you have, okay? And we have the production limit. It says if you are not using the machine, x sub t will be 0, right? So this is like a big M type of constraint, right? If xt is 0, then yt has to be 0, okay? We also have some initial variable constraint. Let's just assume the first time period we have 0 storage, then the storage and the production must be greater than or equal to 0. X is a binary, right? This should be a pretty straightforward problem. Okay. Yeah, so now let's switch gears and talk about the scheduling problem, right? This problem is very ubiquitous. It not only applies to chemical engineering, but in other areas as well, right? So the idea is you have a number of units. So you can think about those units as some machines you have. Those are parallel units. They may be different, but they can complete a set of tasks one to n, right? Okay, maybe when you are in, let's say, primary school, you solve this type of problem, right? You have, let's say, 2 pans, and then you are cooking pancakes, right? How can you cook the pancakes faster, right? The 2 pans you have are the 2 machines you have, right? Something like that. So now you have m different units, and if you assign a given task to a given unit, then the processing time is called PIM, right? Let's assume all those units can be the same or they can be different, right? And then if you assign a task to a given unit, it may have different processing time. And now the idea is that we want to find an optimal way of assigning tasks to the machines such that you can minimize the make span. The make span is the so-called completion time. You can think about you have this number of jobs you want to complete. You want to take the least amount of time to finish all those jobs, right? So now how do we assign those to the units? Okay. So this problem appears to be very simple, but it has been proved that if you only have 2 units, this problem is already NP hard to solve, right? As the number of jobs goes to infinity. This is actually a pretty hard problem. Now, how do we solve this problem, right? We are minimizing the make span, right? So let's define a variable called make span, but then later on we will put that into the constraint to actually give it a definition. Now we define some binary variables, xim, it is equal to 1 when the task I is assigned to unit m, right? And PIM is a parameter. It denotes the processing time of task I on unit m, okay? All right, so first of all, we need some constraint to express what the make span is, right? So I would argue that the make span is a time that take you the longest to complete the job over all the machines, right? So let's say if you have two machines, the first machine may be done very quickly, right? Then the second machine may take longer time. But the make span has to be greater than or equal to the completion time over all the machines, right? This is what it says. So if you sum over PIM, XIM, this part is the amount of time to complete the job to complete the jobs on machine. Oh yes, it should be a machine M. Right? Since we are talking about the completion time of all the jobs, then the total make span should be greater than or equal to all those completion time over all the machines, right? And we need to have some assignment constraint. You need to assign each of the job to at least one machine, right? Actually, we just assume one machine is enough to complete each of the job, right? So that's what this constraint says. If you sum over all the machines for each task I, then it has to be equal to 1. And then we have some non-negative and binary constraint. That's it, right? This is a very, very simple problem, but very difficult to solve, actually. Is it clear? Okay. Yeah, so now let's make the problem a little bit more complicated. Remember in the previous case, we don't care about the sequencing of the jobs, right? Or we don't care about which jobs go first, which jobs go second. We only care about this assignment problem, right? How do you assign the jobs to the machines? Then you just sum over all the time, that's it, right? We don't care about which jobs should be processed first, which should be second. But what if some of the jobs have start and due dates, right? Start meaning that, let's say if maybe you are operating a given supply chain problem, then you are keep receiving orders from the customers, right? But maybe until a certain point, you don't know all the orders, right? You only receive the orders at a given time period. That will be like the release days of a certain task, right? Or maybe you are receiving some materials from upstream producer. You can only start processing the job after they deliver the upstream material to you, right? And each of the job may have different due dates, right? Some of your customer may need the order sooner than other customers, right? So without loss of generality, let's assume each of the job have a release date and a due date. And then you will see that with this type of a specification, it makes the MILP formulation much more complicated. Okay, so now we are dealing with decision variables. If task I is assigned to unit M, then you have xm equals to 1. And here, let's assume we define a continuous variable called TSI. That means the start time of task I, right? We have to define some continuous variables to enforce a constraint that the completion time of a given job is within the due date, and the start time have to be after the release date. Okay. And since we are talking about due date and release date, the sequence will matter here, right? We care about which task goes first, which task goes second to describe the processing time. So for this complication, we are defining a new set of binary variables, xi and I prime. It equals to 1 if task I starts before task I prime on a given unit and 0 otherwise. Okay. I have to caution that the key here is they both start on the same given unit. Because if they are processed on different units, you don't care about that sequence, right? They don't interfere with each other if you assign 2 jobs to 2 separate units, right? It only matters if 2 jobs are assigned to the same unit, right? Then you have to decide which of the jobs should be completed first, right? You will see that in a second. And here's the objective, which is trivial, the same thing we talked about before. The hard thing here are the constraints. All right. Okay, so the first constraint is easy to understand. It says the start time must respect the release date of the job, right? So that's why the start time, RI denotes the release date of job I. Okay, maybe I forgot to put it here. So the RI is the release date or release time of job I, right? You can only start a job after the job is released. Okay. And if you have the early start time, you will also have the latest start time, right? Okay, so that says if you assign job I to machine M, right, then the processing time will be PIM, right? So if that happens, you have to start the job before the due date minus the processing time, right? Otherwise, you wouldn't be able to finish the job on time. So you need to have this summation here because the job is assigned to one of the machines, although you don't know what are the optimal ways to assign the jobs. Okay, and this constraint we've talked about before. You have to assign each task to exactly one unit, right? So the first three should be easy to understand. And any doubts here? Okay, yeah. And then we also have a redundant constraint, which says if you take into account the total processing time of the jobs that are assigned to a given machine, they have to be between the maximum make span you can allow, right? So if you take the maximum over all the due dates, that will be the latest due dates, right? So if you take the minimum over all the release date, that is the earliest release date over all the jobs, right? And if you take the difference of the earliest release date and the latest due date, we are talking about the maximum make span you can have, right? So that says for each of the machine, the total processing time must be within this make span. Okay, yeah. So this is a redundant constraint, but it helps you to tighten the LP relaxation of the problem. Yeah, so now it comes to the hard part. We will apply some of the logic we talked before in previous lectures, right? So in order to really calculate the start time, we need to consider which jobs is processed first, which is second, right? In order to do that, remember we have defined this logic variable yi prime, which says, if job I precedes job I prime, then yi prime is 1, if not otherwise, right? Okay, so what are those logic constraints here? The first thing is if xi m and xi prime m are true, then we have one of these yi prime I is true, right? Remember I said that it only matters if you assign two jobs to the same machine, right? If you assign the two jobs I and I primes to two different machines, their sequence doesn't matter, right? Because they are using different machines, you don't care about which one gets processed first, right? It only matters if both xim and xi prime m is true, meaning that job I and I prime are assigned to the same machine, okay? So here, if you write out this logic that says, if xi m is true and I prime m is true, then that implies yi I prime or yi prime I. Okay, so the first part of this logic means that both I and I prime are assigned to machine M, right? So if they are assigned to the same machine M, then you start caring about their sequence, right? Which one goes first, which one goes second, okay? So that implies either I is before I prime or I prime is before I, okay? So let me go back again. Recall that the definition of yi prime equals to 1 if task I is before task I primes on a given unit, right? The key is it has to happen on a given unit, right? If they are happening on two different units, then you don't care about this, right? Okay. Okay, any questions with this logic expression here? This is a key to the scheduling formulation, right? Yes?
So essentially, like, there should be like a third subscript there for like machine M. Is that a way to think about it? Like for the prime, the yi prime, that only applies to
Yeah, that's a very good point. So you can try to formulate the problem with 3 subscripts, right? There are different ways of formulating this problem. That's a very good way to think about this. In this formulation I talk about, it is a very smart way of avoiding the 3 subscripts, right? Of course, if you have 3 subscripts, that significantly increase the number of binary variable, right? Here it avoids doing that. You can actually think about how you formulate that with 3 subscripts, and then you appreciate this more maybe. Okay, here it doesn't do that. Okay, it only says if this occurs on a given machine, then one of these guys is true, and then you have to enforce this logic for all the machine M. Right? Okay. Yeah. So now we have a logic proposition. How do we convert it to a mixed integer constraint? That's something we've learned in previous lecture, right? Remember, we just converted to conjunctive normal form, right? Then you can express it as mixed integer constraints. Okay, so how do we convert this to conjunctive normal form? First of all, we have to remove the implication, right? So there is an implication you can remove by taking the negation of the first proposition. That will be negation of xim and xi prime m, or yii prime over, right? And then you can apply this thing called De Morgan's law. That will be the negation of xim. Right, so now you are at this particular form. Oh yeah, so I'm missing a negation here, right? So you are at this particular form, which is already a conjunctive normal form, right? You only have the OR operator, right? So all those are OR operator. That means the sum of all those logic propositions have to be greater than or equal to 1, right? At least one of them is true. So that means 1 minus xi m plus 1 minus xi prime m plus yi prime plus yi prime I has to be greater than or equal to 1, right? At least one of those logic is true. And you can simplify this a little bit, you will arrive at this formulation here. Okay? So we spend some time to derive this logic, then we will be using this logic variable yi prime I, right? Recall that when yi prime equals to 1, then that means the job I have to start after, job I prime can start only after job I is processed, right? So if yi prime is 1, then we have this thing is true. As a matter of fact, you can formulate this as a big M type of constraints, right? So this is the start time of job I prime. This is start time of job I. And this is like the processing time of job I. If yi prime is true, then we have something, so yeah, maybe write it down. This is the processing time right? So this yi prime is equal to 1. That means job I and I prime are assigned to the same machine, right? We don't know which machine it is, but we enforce this logic for all the machines, right? So if they are assigned to the same machine, then this part of the big M will be equal to 0, right? Then that we can enforce this constraint I prime can only start after job I is done. Okay. Okay, so you can try to absorb it a little bit after class, and then you kind of appreciate why it only need two subscripts. Okay. Yes?
Going back a little bit, why did we negate the condition that we had before?
Oh yeah, so this is just the formula of implication. Yeah, so if you have A implies B, this is equivalent to either A is not true or B is true, right? Because A implies B means if A is true, B must be true, right? So that says either B is true or A is not true.
And then we used De Morgan's theorem.
Yeah, exactly, yeah, okay. Yeah, so now I'm going to talk about the so-called unit commitment problem. It's a problem gets solved on a daily basis by power producers. Right? So here in the United States, it's divided into different regions. For example, Texas is a region by its own. Here in Indiana, we are in the so-called Midwest ISO. So all the Midwest states form like a coalition. Then we coordinate the use of electricity within this particular region. Right? So you can imagine there are hundreds or thousands of electricity generators in the whole Midwest, right? And there are different customers who needs electricity. But then how do we decide how much power we produce on a given hour, right? The answer is we solve an MILP problem in practice, okay? Yeah, so this is a so-called unit commitment problem. Actually, if you listen to some talks by some electrical engineers, the matureness of those MILP solver play a very significant role in power system operator, right? They argue that if you can decrease the optimality gap of the MILP problem by, let's say, 0.1%, we are talking about billions of dollars, right? If you can improve those optimization methods a little bit, you can save quite significant amount of energy, right? Because think about all the powers that are used in the whole United States. That's a huge chunk of energy, right? Okay, so the unit commitment problem involves determining the schedule of those power generators, right? When you should start the power generators, when you should shut down the power generators, right? And over a planning horizon, this planning horizon is usually 24 hours. Usually what happens in practice is that before tomorrow, we are going to solve an MILP to decide a rough schedule of the startup and the shutdown of units. Okay. So here are all the parameters. You don't need to remember all of those for now. The idea is to give you some sense how this optimization problem works. But we have fixed cost and the variable cost of the generating units G, right? So the fixed cost means that whenever a unit is on, you have to pay a fixed cost, okay? And then the variable cost means that it is proportional to the amount of power you produce, right? It's very easy to think about. If you have a natural gas generator, the more power you want to produce, the more natural gas you need to consume, right? And that's like the variable cost. And we also have the startup and the shutdown cost of the generator. If you shut it down when you start up, you need to pay a fixed cost. For each of those generator, you have a minimum and a maximum power output of a given unit, right? RU and RD are the so-called ramp up and ramp down rate of a given unit, right? So let's say a given unit is producing power at, let's say, 10 megawatts per hour. But if you want to ramp it up to be 50 megawatts per hour, maybe you cannot get it down within a single hour, right? That's limited by the ramp rates of the generator. For example, if the ramp rate of the generator is 20 megawatts per hour, then if you want to ramp up from 10 to 50, you need 2 hours to ramp it up, right? That's so-called ramp rate. And similarly, you have a ramp down rate of the generator. And PD is the power demand at time t. RD is quite, how do I say? It's quite a jargon in power systems. It is so-called the reserve demand. What it means is that I'm now solving a problem for tomorrow, right? But maybe I don't have a good forecast of the demand for tomorrow, right? So I want to reserve some additional capacity such that I'm safe if my prediction is wrong, right? So if you don't have the reserve, you will have a blackout on some of the days, right? You are underproducing those power, okay? Yeah, and then in order to solve this problem, we define some variables here. We should pay particular attention to those binary variables, right? So UGT decides whether a generator is on or not at time t. And YT says if the generator starts up, and Z says if a generator shuts down at time t. P sub GT denotes the power output of a unit G at time t. Okay, so the objective function include all the different types of cost. This is the fixed operating cost. This is the variable operating cost. Then we have the startup and shutdown cost of those generators. Okay. And then you can check the first constraint is related to the startup and the shutdown condition, right? Remember, UGT denotes whether a generator is on or not at a particular time, right? So if a generator is not on time t minus 1 and it's on time t, that means you are starting up on time t, right? If that is the case, you will have YGT equals to 1 because YGT denotes whether a generator starts, right? On the other hand, if a generator is off other way around. If a generator is on at time t minus 1, but you are shutting it down at time t, right? That means the Z variable which denotes the shutdown must be 1 at time t, okay? So this is like, if you wish, a mass balance constraint for the generators, right? You have to balance the logic of the on and off of the generators. Okay, and then of course a unit cannot start and shut down simultaneously, right? You either start up or shut down, or you keep the generator being on, right? That's why this constraint says. Generation limit constraints means that once the generator is on, there is a maximum and a minimum amount of power you can produce. Okay. And then we have something called the ramp up and ramp down rates, right? Okay, remember the definition of ramp up and ramp down rates are the maximum capacity you can increase at a given time and the maximum capacity you can decrease at a given time, right? So here it is the PGT minus PGT minus 1 is like taking the difference of the ramp up, right? So if you want to increase the capacity, then the capacity difference is determined by PGT minus PGT minus 1. Okay. Oh, not the capacity, the production, right? So here, it is a little bit complicated because when you want to increase the production level, there are two cases that can occur. First case is that the generator was off in the previous time period, but now you just started, right? And then if you just started at time t, the ramp rate is this ramp rate RGSU here. But on the other hand, if the generator was on in the previous time period, that says the UGT minus 1 is 1, then we are talking about a slightly different ramp rates, right? That's because of the physics of the generator. Because if the generator was not on in the previous time period, the ramp rates are different than if the generator was on in the previous time period. That's why you have two different things on the right-hand side. And similar, you have a ramp down rates type of constraints. We also need to satisfy the demand for time t. This is trivial, right? Sum over all the production should be equal to the demand. And we also have something called the reserve requirements. You can kind of ignore this constraint. This is some jargon related to power systems. The idea is our maximum capacity has to be greater than equal to the demand plus some sort of reserve, right? The reserve can be determined by some heuristic. You want to make sure your system work even though the demand is much higher than what you predicted, okay? And you enforce the binary constraints. Any questions here? Okay. So finally, let's talk about the most interesting problem, right? A chemical engineering problem. Are all the audience chemical engineers today? Okay, great. Yeah, otherwise I need to give a 1 minute lecture on what chemical engineer is. Okay, yeah, but anyways, so if you think about what you are doing in your senior design class, I guess most of the people have taken a senior design class in their undergrad, right? The idea is that you want to use some raw materials to produce some final product, right? And then you want to design a chemical flow sheet that does that in the most cost-optimal way, right? There are different ways you can design a given flow sheet, right? You can think about there are different alternatives. Let's say if you want to separate a mixture, there are different ways you can design the distillation columns, right? And then there are different ways you can design the separation system. You either use distillation or you use membrane, right? What would be the most effective way of achieving that, right? Then you can formulate that as an optimization problem to pick the optimal way from the so-called superstructure. Okay. Yeah, so this problem here is the so-called process synthesis problem. That means that you have different unit operations you can use, but you want to pick the set of unit operation or the combination of unit operation and equipment that achieve your final goal in a most cost-effective way, right? And in order to formulate this problem as an optimization problem, there is a very nice philosophy introduced called the superstructure optimization. Right? I believe it was invented by my PhD advisor, Professor Ignacio Grossman. So they invented this idea called superstructure optimization. So the high-level idea is that you have numerous ways of designing a given flow sheet, right? But then you will invent some superstructure which can encapsulate the set of all the feasible alternatives, right? So imagine there are a million ways of designing a flow sheet to convert A to B, right? Including reaction and separation. And then you need to define a superstructure, code superstructure that incorporate all those a million different ways of designing this flow sheet. And you design a MILP formulation to pick the optimal one from this superstructure. Okay, this is an abstract way of describing that. After I show you a very trivial distillation example, you will quickly understand what I mean. Okay, so there are 3 steps. First, design a superstructure, then translate the superstructure into a mathematical programming model, then compute the optimal superstructure by solving the optimization model. Okay. This sounds very abstract, but if you look at a simple example, which is a distillation sequence synthesis, okay. So let's suppose we are given mixture A, B, C, and then we want to get pure component A, B, and C separately, right? And there are different ways you can design the distillation columns, right? Let's suppose each time you have a distillation column, you can only get one separation, right? So if you suppose maybe A is the lightest component of C, so let's say on the top is the light component, the bottom is the heavy components, right? Okay. So then the first time you have a distillation column to separate A, B, and C, there are 2 instances that can occur, right? You can have a column that separate A, B from C, right? So the light components are A and B, the heavy ones are C. And the other alternative is that you first separate the lightest component A, and BC will go to the bottom of the distillation column, right? So that's the 2 alternatives you have for designing the first distillation column, right? Then if you produce AB, then you have no choice anymore but just separate A and B, right? And similarly here, if you have BC, there you have no other choice but just separate B and C, right? As you can see, for this very simple problem, if I have this so-called state task superstructure, this superstructure outlines all the alternatives of separating ABC into pure components, right? Although there are not many options, but as you can imagine, if you have 10 different components, this superstructure will be very large, right? At the first column, you will have, let's say, 9 different ways of separating them. And then you, in total, I guess you have around n factorial number of ways of designing distillation columns, right? So, okay, maybe even bigger than n factorial here. But this small problem should give you an idea of what is a superstructure, okay? Now we are going to formulate an optimization problem to select the optimal sequence from the distillation, from the superstructure. But this is a very trivial problem, right? There are only 2 alternatives you can pick. You either first separate, take this path, or you just take this path, right? There are only 2 alternatives. But for a bigger problem, there can be, let's say, n factorial number of alternatives, right? How do you formulate this as a MILP problem and then let the algorithm to help you pick the optimal one? Okay. Then the formulation is also quite easy here if we ignore the most complicated physics, right? Of course, if you include all those mesh equations in distillation, this will be a huge problem. But for the sake of the argument, we just assume we have a perfect split in each of the column, right? Yeah. So let's use variables f to denote the flow rate for each of these streams. And we use variable y to denote a binary, the binary variable y denotes whether this column exists or not, right? If y is 0, you assume you do not have this column, okay? And there are only 3 constraints in this problem. The first one is mass balance, right? For example, at this node here, you are splitting the total flow into F1 and F2, right? And at this particular column here, we are splitting AB from the mixture ABC, right? So if you already know the mass or mole fraction of AB, then we are talking about a constant C superscript AB here, right? So F3 and F1 relationship can be determined by this simple linear equation here. If you assume we already know the mass fraction, and we assume you have a sharp split, right? Each time you just split the stream, you get pure C and AB. Okay. And finally, we have logic constraint, right? If the column is not built, then the corresponding flow must be 0. Right? This is what it says. If yk is 0, then f is 0. Otherwise, you have sort of like a big M type of upper bound. And then you can calculate the hot and cold utility assumption. We just assume the hot utility is proportional to the flow rate at the reboiler, and then the other is the proportional to the condenser. Okay. Yeah. So here's the whole formulation. You are minimizing this part will be the utility cost. Then you have a variable cost of each of the column and the fixed cost of each of the column. Right? Okay. Any questions? Yes.
If you're doing with the chemical engineering problem, don't you have to consider that this has to be non-linear?
Yeah, exactly. That's a very good point. If you want to consider some more complicated physics in this distillation column, right? Let's say if you have some mesh equations, or if you want to consider something like heat integration into the distillation column, this problem will be highly nonlinear, right? Remember when you talk about things like heat integration, you talk about what is that called? Log mean square temperature or something like that. You have some log term and so forth, right? That's why the chemical engineering synthesis problem is very hard to solve, right? I believe Albert is an expert on that. You are working on some of those synthesis problems, okay? Yeah. So this is just to give you an idea of what a superstructure is, right? You outline all the alternatives of a given flow sheet, and then you pick the optimal one from them using optimization, right? This occurs in all the chemical engineering problems, not just distillation column synthesis. If you are dealing with things like reaction networks or heat exchanger networks, all those problems can be formulated as MILP or MINLP problems.